Okay, in this video, we are going to start note 6 of Calc AB. It's about implicit differentiation, which is really, I swear to you, it's just the chain rule. So if you know what you're doing with the chain rule, you'll be okay with this. Let's see what it looks like, though, because it looks and feels a little different at first. So we're going to start with an idea that seems a little weird. We're going to do the same problem basically two different ways. In the second way, I'm going to demonstrate kind of what it means to use implicit differentiation. So for the first problem, we want to find the derivative of y equals 1 over x at -1, -1. So -1, -1 is a point on the curve. You'll find in textbooks, there's a lot of problems about this concept that don't actually make sense. The point that they give you doesn't appear anywhere on the curve. Hopefully I've avoided that issue here. But if you try to check your answer two different ways, you might end up not being able to. And the reason would be exactly that, like the point isn't on the curve. So it doesn't make sense to find the slope at a particular point that's not on the curve. So let's do this. All right, so I'm going to say dy dx is -1 over x squared. So when I see this thing, I always immediately think x to the negative first, so that I can just power rule it and kind of like think it through in my head. So that's the derivative, and then dy dx such that x equals -1 is going to give me -1. Not a big deal. Okay. Now let's see this problem. All right, so find the value of dy dx given that x times y is equal to 1. So we're going to do this a little differently. It's the first time we've done it. We're going to take the derivative implicitly. So what I'll do, I'm going to take the derivative of both sides with respect to x. So I'm going to say d dx of xy equals d dx of 1. So I'm taking the derivative with respect to x of both sides. Hold on, I got to make my computer not go to sleep here. Activate for indefinitely. So I use an app that's called Caffeine on my Macs to make them not go to sleep. And one of the options is indefinitely, and I always wanted to say infinitely, but it doesn't. It just says indefinitely. All right, so now let's do it. So this is a product, right? So we're going to need the product rule. So the derivative of, so it's first. Now, what's the derivative of y with respect to x? It's dy dx. So first derivative of the second is y, the derivative of that is dy dx, plus second, which is y. Derivative of x with respect to x is 1. And then the derivative of a constant is 0. That's actually, once you know what you're doing, that's the most common mistake that I see my students make. Derivative of a constant is 0, so try to remember that. Okay, so I want to find dy dx, so I'm going to solve this for dy dx. So dy dx is going to be subtract y, divide by x. So this looks a little different, but I do know this point right here. So I'm going to substitute that, and this time it makes sense that I need to know x and y because there's an x and a y. So I'm going to say such that -1, -1, which is negative, -1, -1, -1. So let's zoom out. We got the same answer two different ways, but we got the same answer, and that's the key thing. So the process we just went through on part B is called implicit differentiation. So it's when you don't explicitly solve for y, and you still find dy dx. So we're going to use this a lot. And this example is pretty much the quintessential thing. I mean, you're going to use the product rule almost all the time. You're going to have to use the chain rule a lot. But it's not that bad. Let's see if we can do it for this. So for the previous one, I mean, like, why do it, right? If you were given part B, wouldn't you just divide both sides by x anyway and then do part A, essentially? Well, what if you have a problem that looks like this? How are you going to solve that for y? Right? So I don't even know where to start with like what my game plan would be. Maybe subtract x squared y from both sides and then what? Inverse sine, but now your y on the right-hand side is inside of an inverse sine. You can't do it. Like you can't really like extricate that y from the situation. This is a classic example of where you would definitely want to use implicit differentiation. So let's do it. So what I usually do, I try to always remember this. Sometimes I forget. I'm going to write that we are finding d dx. So why are we finding that? Because of that. If that said d dz, I'd be doing d dz of both sides. Totally different problem. D dx of x squared y plus sine of pi y, I like saying pi y, equals d dx of 4. Okay. And then, all right, so left-hand side is pretty exciting. The right-hand side is not very exciting at all. Left-hand side, so it's the derivative of x squared y. That's a product rule problem. So first, derivative of y is dy dx, plus second, which is y. The derivative of x squared is 2x. Okay, that's your product rule part. So let me highlight that in a color. So this part gave us this from the product rule. And now we're going to take the derivative of sine of pi y using the chain rule. So the derivative of sine is, so it's going to be, I'm going to say pi cosine of pi y. But the chain rule says times the derivative of the inner function. What is the derivative of pi times y with respect to x? It's dy dx. Also, I kind of did that wrong if I were going to make this make the most sense to you. So I'm actually going to go back and do it again in a way that I think is a little more sensible if you've never really done this before. So here it is. The derivative of sine of something is cosine of that thing, right? Because I can just blow through these, but like if you're not following and you're not learning what it is, then what's the point? All right, so it's derivative of sine of something is cosine of that thing times the derivative of that thing. Derivative of pi times y with respect to x is pi times dy dx. So we'll do that. I think that's better. And then the derivative of a constant is 0. Number one mistake that I see people make. Okay, so let me highlight slightly different color. This gave us this. Just to keep track of what's what and where things are coming from. All right, now we want to solve. Well, do we want to solve for dy dx? Or do we want to find the value of dy dx? I think we want to find the value. So what I'm going to do, I mean, I know we want to find the value. That's the problem. So I'm going to say at the point 2, 1, and now I'm going to substitute for x and for y. So every x I see becomes a 2. So this will be 4 dy dx plus 1 times 2 times 2, so plus 4, plus the cosine of pi is -1, so negative pi dy dx. Okay, and we want to solve, and that equals 0. We want to solve for dy dx, so I'm going to, all right, I'll do more steps than I usually do. Usually I like to just subtract 4 and then factor and whatever. I usually do it in one shot, but I'm going to take dy dx out of both of these, get this, and then we can say that dy dx is -4 over 4 minus pi, which you're done, right? There's no reason to go further than that, but you might say, or, because this happens just a lot with implicit is why I'm doing it. Otherwise, there's no reason to do this. Take the negative from the numerator and distribute it to the denominator, and you get 4 over pi minus 4. Like, they're equivalent, doesn't really matter. But either of those is a fine representation of the derivative. So this kind of will summarize for you what we're doing. So take the derivative of everything you see with respect to the independent variable. So the independent variable you can tell because you're doing like dy dx, dx in that kind of denominator, x is the independent variable. So with respect to the independent variable, don't forget the derivative of a constant is 0. And then if you're finding the derivative at a point, plug in as soon as you can. If you are asked to find dy dx, then you do your algebra. So these are the two most common mistakes that I see. Derivative of a constant is 0. I see people forget that. And then also forgetting the chain rule. We haven't actually seen one yet where you could have forgotten the chain. Well, no, we did. Right here, the derivative of sine of pi y, right? Have to use the chain rule on that. Don't forget the chain rule. I'm going to show you right now, a way that you can use your calculator for this, it's like kind of early in the notes, but I think that the sooner you see it, the better. So let's see what we can do here. Okay, so I'll start a new document. New document. So I want menu and then option 4 for calculus. Press up, and again, implicit differentiation. Such a common thing that it's built in. Imp diff. I like to just type it. So here's what you do. You type in your relationship. So x times y equals 1. Now you're going to do comma x because that's the independent, comma y because it's the dependent variable. Press enter, and it gives it to you. Now, if you need to evaluate it, you can do such that x equals -1, and then such that y equals -1. I think that's the fastest way to like evaluate it at a point, like do one coordinate, then do the other coordinate. You also could have done and y equals -1, do it in one shot, but like it's really annoying to type and. I'm gonna check the other one too. So imp diff or, right, menu, option 4, press up, implicit. Okay, x squared. So when you multiply two variables, it is not optional to put the multiplication sign. So like when I did the first one, I did x times y. I couldn't just type xy because then the calculator thinks xy is a variable, and it's not in this case. This multiplication I actually don't need because the exponent makes it very clear to the calculator what's going on. Safer to put it though. Plus sine of pi times y equals 4. X is independent, y is dependent. Press enter. Now, we never even did that part by hand. That's what we would have gotten if we solved for dy dx. Now what I'm going to do is such that x equals 2, okay, and then such that y equals 1. And press enter. And you can see the calculator give the second answer that we found, 4 over pi minus 4. It's just really common, so be on the lookout for that. All right, I'm gonna go back to the notes, and then I will end this video and come back and just keep going.